You are welcome. In the previous video, we have treated direct substitution and factorization techniques. In this video, we are going to talk about another two techniques of evaluating limits, which are reduction power and L'Hopital's rule techniques. If you have not watched the previous video, kindly click on the description below and navigate to the playlist inside the description and click on the calculus playlist link. Then it will lead you to calculus playlist where you can enjoy all video based on calculus. Now let's look at some basic operations in evaluating limits. Now we have two forms of operations. These are determinate and indeterminate form. Now let's look at the determinate form. For addition operation, we have infinity plus infinity is equal to infinity, and infinity plus c, which is constant, is equal to infinity when c is not equal to minus infinity, when c is equal to constant. For subtraction operation, we have minus infinity is equal to minus infinity. Then minus infinity minus c is equal to minus infinity when c is not equal to minus infinity. Then for multiplication, infinity times infinity is equal to infinity. Then minus infinity times minus infinity is equal to infinity. Then minus infinity times infinity is equal to minus infinity. Then constant c times infinity is equal to infinity when c is greater than 0, and c times infinity is equal to minus infinity when c is less than 0. Now for the division operation, we have infinity over c is equal to infinity. This will equal when c is greater than 0 and c must not equal to infinity. Then minus infinity over c is also equal to minus infinity when c is greater than 0 and c must not equal to infinity. Then c over infinity is equal to 0, and also c over minus infinity is also equal to 0. Now all the listed operations are the determinate form, and this means they have solution. Now let's talk about the indeterminate form, which have no solution. Now when we have infinity minus infinity, these have no solution. Then plus or minus infinity over plus or minus infinity, these have no solution. Also 0 over 0 is undefined. Then 0 raised to power 0 have no solution. Now let us move on to how to evaluate limits using reduction of power techniques. Now let's start. Example A. If we have limit when x tends to infinity, 5x raised to power 3 minus 6x raised to power 2 plus 1. Now before we solve this using reduction of power, let's try to use direct substitution. So 5 into infinity raised to power 3 minus 6 into infinity raised to power 2 plus 1. This is equal to infinity minus infinity plus 1. So infinity minus infinity is indeterminate. Therefore, by using reduction of power, x raised to power 3 is the highest x term. So to do this, we have to factorize x raised to power 3 out of the bracket to reduce the power. Now x raised to power 3 into 5 minus 6 x raised to power 2 will be 6 over x, and this one will be 1 over x raised to power 3. Now let's substitute for infinity. Infinity raised to power 3 into 5 minus 6 over infinity plus 1 over infinity raised to power 3. This will be infinity raised to power 3 is equal to infinity, and 6 over infinity is equal to 0, and 1 over infinity is equal to 1 over infinity raised to power 3 is equal to 0. So this will be infinity raised to power 3 into 5 minus 0 plus 0, and this will be infinity times 5, and infinity times constant is equal to infinity. So this is the answer to this question. Now let's move to example B. Now when we have limit when x tends minus infinity for 3x raised to power 7 plus x raised to power 6 over 2 minus x raised to power 2 plus x. Before using reduction of power, let's try to use direct substitution. Now we have 3 into minus infinity raised to power 7 plus minus infinity raised to power 6 over 2 minus into minus infinity raised to power 2 plus minus infinity. Power of 7 is even, so we have minus infinity plus 6 is even, so we have infinity minus infinity minus infinity. So we can say that minus infinity plus infinity is indeterminate. Now we can say that the highest x term is x raised to power 7. So we have limit when x tends to minus infinity, x raised to power 7 into 3 plus 1 over 2x minus 1 over x raised to power 5 plus 1 over x raised to power 6. So we have, let's substitute now. We have minus infinity raised to power 7 into 3 plus 1 over 2 into minus infinity minus 1 over minus infinity raised to power 5 plus 1 over minus infinity raised to power 6. Now for power of 7 we have minus infinity into 3. All the rest will be equal to 0. So therefore we have minus infinity times 3, so it will be equal to minus infinity. Now let's move on to another example. Example C. If you have limit when x tends to infinity of x raised to power 6 minus 2x raised to power 3 plus x raised to power 2 minus 5 all over 2x raised to power 5 minus 4x. Now to solve this using reduction of power for fractional function like this, we have to consider the highest x term in the denominator of fractional function, in which in this fractional function the highest x term is x raised to power 5. Then we will use this term to divide every other terms in both numerator and denominator. So we will have limit when x tends to infinity into x raised to power 6 over x raised to power 5 minus 2x raised to power 3 over x raised to power 5 plus x raised to power 2 over x raised to power 5 minus 5 over x raised to power 5 all over 2x raised to power 5 over x raised to power 5 minus 4x over x raised to power 5. Then the term will cancel each other. 5 will cancel 6, remain 1x, and this one will remain x raised to power 2, and this one will remain x raised to power 3, and this one as well, this will remain x raised to power 4. Then it will remain the limit when x tends to infinity into x minus 2 over x raised to power 2 plus 1 over x raised to power 3 minus 5 over x raised to power 5 all over 2 minus 4 over x raised to power 4. Then let's substitute for x. We have infinity minus 2 over infinity raised to power 2 plus 1 over infinity raised to power 3 minus 5 over infinity raised to power 5 all over 2 minus 4 over infinity raised to power 4. Then all this will be equal to 0 and it will remain infinity over 2, which is equal to infinity. Now let's move to the next example. Example D. When we have limits when x tends to infinity, 3x raised to power 4 plus 2x minus 1 all over x raised to power 4 minus x plus 2. Now, let me show you a trick to solve this using reduction of power. The trick is that we have to consider the highest x term in the numerator and the denominator. In this example, we have x raised to power 4 in numerator and the denominator. So, just take these terms with their corresponding coefficient. So, we have limit when x tends to infinity, 3x raised to power 4 over x raised to power 4. So, this we cancel this. So, the value of this question is 3. You can check to confirm the answer using the reduction of power. Now, let's move on to example A. If you have limits when x tends to infinity, x raised to power 5 plus 2x raised to power 4 minus 2x all over 4x raised to power 6 plus 2x raised to power 2 minus 1. So here the highest power of x is 5 and 6. So our limit will be limit when x tends to infinity, x raised to power 5 over 4x raised to power 6. So this will cancel each other out. Therefore, let's substitute for 1 over 4x. And the final answer for this will be 1 over infinity, which is equal to 0. Now, let's move on to another example. Example F. Limit when x tends to infinity into 5 minus x raised to power 2 plus 2x raised to power 3 minus x raised to power 6 all over 4x raised to power 5 plus 2x raised to power 4 minus 2x. Now, don't be deceived by the numerator. The highest x term is still x raised to power 6 and the denominator is 4x raised to power 5. So we have limit when x tends to infinity into minus x raised to power 6 over 4x raised to power 5. So this will cancel the power of 6. Then this will remain the limit when x tends to infinity minus x over 4. Now let's substitute. We have minus infinity over 4, which is minus infinity. Now let's move on to the next technique, which is L'Hopital's rule. Now, to use a L'Hopital's rule, we have to differentiate both numerator and denominator and substitute the limit term. Then, if the substitution leads to an indeterminate result, then we will have to continue differentiate and substitute on the result does not yield an indefinite form. That is, if limit when x tend to a function of x over function of g is equal to 0 over 0 or plus or minus infinity over plus or minus infinity, it is undefined and indeterminate. So we will differentiate both function of x and function of g, and if the same thing repeats itself and equal to 0 over 0 or this one as well, so we still continue and do the second derivative of f of x and g of x, and it will continue like this until we have a determinate form of result. Hope is clear. Thank you. And we have to know that L'Hopital's rule does not work for products but only work for quotient function. Now let's look at some examples. Example A, we have limit when x tends to 1, x raised to power 2 minus 1 over x minus 1. Then let's try to use direct substitution. So this will equal to 0 over 0. You can see that this can be our solution by using direct substitution. So let's use the L'Hopital's rule. So derivative of x raised to power 2 minus 1 over derivative of x minus 1. And remember that if y is equal to ax raised to power n, the derivative of y will be an multiplied by x raised to power n minus 1. So let's use that for this. We have the limit when x tends to 1 is equal to 2x over 1. Let's substitute now. We have 2 times 1 over 1, which is equal to 2. This is our value. To check for this, we can still use another method. We can use factorization method. So the limit of when x tends to 1, the numerator is an example of difference of 2 squares. So we have this over x minus 1. So this will cancel each other and it will remain 1 plus 1. This is equal to 2. Now another example. When we have limits when x tends to infinity, x raised to power 3 minus 2x raised to power 2 plus 4 over 5x raised to power 2. Let's check for direct substitution. So we have infinity raised to power 3 minus 2 into infinity raised to power 2 plus 4 over this. So this will equal to infinity minus infinity plus 4 over infinity. And there's no solution for infinity minus infinity. Now let's solve it using L'Hopital's rule. So the derivative of numerator will be equal to 3x raised to power 2 minus 4x over 10x. And let's try to substitute for the value of x. So we will have 3 into infinity raised to power 2 minus 4 into infinity over 10 into infinity. So this will equal to infinity minus infinity, which is not correct. So now let's continue. The derivative of this of the numerator will be 6x minus 4 over 10. And let's substitute for the value of x now. 6 into infinity minus 4 over 10. And this will eventually equals to infinity over 10, which is equal to infinity. And this is the answer. Actually, you can still use another method using reduction of power. We have x raised to power 3 over 5x raised to power 2. X raised to power 2 will cancel the power of 3, so it will left x over 5, and this will be equal to infinity. So it's correct. Now, next example. If we have limits when x tends to 0, sin x over x. If we substitute directly, we will definitely get 0 over 0. So derivative of sin x is equal to cos x, and for the x is equal to 1. So therefore, by using the hopital's rule, we'll have limit when x tends to 0 cos x over 1. Now let's substitute now. We'll have cos 0 over 1. So cos 0 is equal to 1. So we have 1 over 1, which is 1. Now let's move on to the next one. When we have limit e raised to power x over x raised to power 2 when x tends to infinity. Let's try the direct substitution. We have e raised to power infinity over infinity raised to power 2, and this will equal to infinity over infinity, which is indefinite form. So let's use L'Hopital's rule. So derivative of e raised to power x is equal to e raised to power x. Now we have e raised to power x over 2x when x tends to infinity. Since we know that numerator won't change and we have x in the denominator, so let's differentiate it one more time. So we will have limit e raised to power x over 2 when x tends to infinity. And let's substitute now. We have e raised to power infinity over 2, and this will equal to infinity. So let's move on to another example. So if we have limit when x tends to 0, 9 raised to power x minus 1 over x. And for this, we have power of x. And to solve this, remember that derivative of a raised to power x is equal to a raised to power x ln a. So this will equals to 9 raised to power x ln 9. For minus 1, it is a constant and its derivative is equal to 0. Now let's solve it. So we have limit 9 raised to power x ln 9 over 1 when x tends to 0. So this will equal to 9 raised to power 0 ln 9, and 9 over 0 is equal to 1. So our answer is ln 9. Now let's move on to another example. So if you have limit when x tends to 0, e raised to power x minus e raised to power minus x over x. And we know that derivative of e raised to power x is equal to e raised to power x. But for this, the derivative of this will be, let's represent minus x as u. So u is equal to minus x, and derivative of minus x, which is du dx, will be equal to minus 1. And for the derivative of e raised to power u, that one will be equal to e raised to power u. So now let's use our chain rule, and this will be the e raised to power u du times du over dx, which is equal to e raised to power u times minus 1. So this will be equal to minus e raised to power minus x. So now let's solve it. The limit when x tends to 0 is equal to e raised to power x minus into minus e raised to power minus x over 1. So this will equal to 0. Minus times minus equal to plus. So e raised to power minus 0. So, and this is e raised to power 0 plus 1 over e raised to power 0, which is equal to 1 plus 1 over 1, which is equal to 2. Now, let's move on to another example. if you have limit when x tends to 0, x ln x. Now for this, we have to rearrange. So we will have limit when x tends to 0 ln x over 1 over x, because x is equal to 1 over 1 over x. Therefore, now let's find the derivative of ln x. But before that, this is equal to this. So derivative of ln x is also equal to 1 over x. So this will be the limit when x tends to 0, 1 over x over derivative of this will be minus x raised to power minus 2. And this is the same thing as limit when x tends to 0 minus x raised to power minus 1 over x raised to power minus 2. And this will be minus x raised to power minus 1 minus minus 2 by using indices. So, and this will equal to the limit when x tends to 0 minus x raised to power minus 1 plus 2, which is minus x raised to power 1, and this is equal to minus 0 raised to power 1 and is equal to 0. Another example, if you have the limit when x tends to minus infinity, x e raised to power x. So let's try to use the rest of the decision. So we have minus infinity e raised to minus infinity, and this will be equal to minus infinity times this, and the answer will be equal to minus infinity over infinity, which is indeterminate. So let's use L'Hopital's rule by rearranging the function. So we have this, that there may not be solution for a selected function. Like in this case, we select x to be our denominator, but there won't be solution for this. Okay, let's check the limit e raised to power a over minus 1 over x raised to power 2. So let's substitute for minus infinity. So we have this, and you can see that now this will equal to 1 over e raised to power infinity by minus infinity. This is indeterminate and this cannot be our solution. So let's differentiate it again. So we have this e raised to power x over this. Then let's substitute. We have e raised to power minus infinity times minus infinity raised to power 3 over 2. And this as well cannot be our solution. Let's see. So you can see it will equal to minus infinity over infinity. So this cannot be our solution. If we still trying this, we still get this particular answer. So let's use e raised to power x power denominator. So this will be limit when x tends to minus infinity x over e raised to power minus x. Now let's differentiate it. We have 1 over minus e raised to power minus x. Let's substitute now. We have 1 over minus e raised to power minus into minus infinity. So this will equal to 1 over minus e raised to power infinity is equal to 1 over minus infinity, which is equal to 0. Now, the last example. When we have limit x sine 2 over x when x tends to infinity. Now let's convert the x to be at the denominator. So we have limit when x tends to infinity sine 2 over x all over 1 over x. So let's find the derivative now. Derivative of sine 2 over x. For this, let u equal to 2 over x. So the u dx will be minus 2 over x raised to power 2. And d sine u dx will be equal to cos u. So by using chain rule, our d sine 2 over x dx will be equal to minus 2 over x raised to power 2 cos 2 over x all over, for this will be minus 1 over x raised to power 2. And in this will cancel this, so it will remain 2. So this will be limit when x tends to infinity 2 cos 2 over x. Now let's substitute for the value of x. So it will be 2 cos 2 over infinity which is equal to 2 cos 0, and the value of this is 2 times 1, which is 2. Hope this is clear. Thank you for watching. We will meet in the next video where we are going to talk about the last two techniques of evaluating limits. Till then, have a nice time.